So good morning, everybody. We're going to start now. I'm Joelle Aubin. I'm the chair of the European Federation of Chemical Engineering Working Party on Mixing. And I'd like to thank you all for connecting to this ceremony for the European Mixing Awards. It's lovely to see that we've had so many registrations for this, webinar series this morning, following yesterday afternoon's webinar, which was really fantastic. Now I'm going to hand over the floor straight away to my colleague, Professor Giuseppina Montante from the University of Bologna. She is the chair of the awards committee of our working party, and she's going to lead the session this morning.
Thank you very much, Joelle. Good morning, everybody. I'm very happy and honored to introduce you this event today. That is for the first time an online event. As you have seen in the program today, we are presenting the two awards of mixing of our working party, the Young Researcher Award and the Lifetime Recognition Awards. Both the awards were established in the year 2000 to give a recognition on outstanding contribution on mixing research and industrial contribution, both to young researchers at the early stage of their career and senior researcher throughout their career. We are used to celebrate this event in the gala dinner of the European Mixing Conferences. And today I would like to thank first Joelle for organizing this online event that will give us the opportunity to celebrate with the winners and listen to their presentations. And I'm sure then that in 2 years' time we will be able to meet and to add their presence in the pictures that we are usually taking during the event in presence. So let's just a few minutes for introducing you the criteria that the committee usually considers for selecting the winners among the nominated candidates that belong to one of the EFCE member countries, of course, as well as the nominators. Of course, we consider excellence in scientific research in mixing, important contribution to the industrial sectors concerning mixing, both for the young researcher and the lifetime recognition awards. Important aspects are, of course, also international activities, networking, and dissemination of the results by participating to the mixing conference. That is something that we value quite a lot. This edition of the awards has seen two new sponsors for both the Young Researcher and the Lifetime Recognition Awards. Brucato is sponsoring for the first time and for the future editions the Young Researcher Awards. Alvin and Nienow are sponsoring the Lifetime Recognition Awards that has been renamed Nienow Lifetime Recognition Awards. We are very grateful to both the sponsors for a very generous contribution, and I'm sure that also the winners of these awards will be honored to receive a prize that is supported by a very important company, literally steering and mixing technology, and Professor Alvin Nienow and Helen Nienow, who are very important personalities in the mixing community, and don't need an introduction, of course. Finally, what I before giving the floor to my colleagues, I would like to introduce you the award committee of the Working Party on Mixing that I'm chairing. Currently, it includes 7 members. 4 of them are past winners of the Lifetime Recognition Awards. You can see here their pictures: Professor Alvin, Professor Joelle Aubin, Professor Alvin, and Professor Michael Boneskis are the 4 past winners that currently in the committee. And we have also 2 industrial members of the Working Party on Mixing that are Joachim Ritter from Bayer and Wolfgang Last from Brucato. Clearly, I didn't put my picture because I'm here. I'm also a member of the committee as one of the past winners of the Young Researcher Awards. I'm chairing the committee, but in the case of this edition, as it's obvious rule of the committee, we step aside every time we have a nomination belonging to our institution or close to our institution. For this reason, Alvin and Wolfgang very kindly accepted to replace me in this role of chairing the committee. Therefore, the acting chair for the Nienow Lifetime Recognition Award has been Alvin Nienow himself, and the acting chair for the Young Researcher Award has been, in this occasion, Wolfgang Last. This is the reason why I will leave now the floor to Wolfgang Last first, who will present the awards to the winner of the Young Researcher Awards in mixing. And I thank you all for participating, and I just announce you that after this, the floor will be of Alvin with the presentation of the Lifetime Recognition Awards.
So thank you, Giusy, for this very kind introduction. We got quite some candidates for the Young Researcher Award, and it was for us as a committee very difficult to follow the criteria, to find the candidates for this criteria you have just mentioned. So getting the PhDs and reading all the details, I was overwhelmed over the very fundamental theses which have been presented in the field of mixing. And for sure, it was a scientific impact and all the publications which in the journals in the field of mixing, which was one of also the main topics for the criteria. And as Giusy has mentioned, ongoing activities in mixing and the industrial significance. I'm very happy and proud to pronounce Lena and Hohl and Francesca Maluta as both worthy for this award. And I'm also happy to have you two here in the group, also from the gender type. So this is and have it equally here in balance. Yeah, if we look on the process, so it was you have seen we were 6 people in the committee to find a good or the best winners of this award, and we were struggling, and at the end it was an even match. And so I'm very happy to have two of those candidates here today. I will start with you, Lena, as you will have the first presentation as well. So looking at your at your thesis, so it is you were especially on uncommon phenomena which are related to steered multiphase systems in the dispersion of fluids. You have taken the characterization of both the mixing and the separation. So it is not always the mixing itself, but also the separation of the processes or the fluids again. And you had a very deep physical understanding of the dispersion and the phase separation in the three-phase system. So you were focusing on the drop size distribution, structure of the dispersion, and in the results of an enormous impact on the separation itself. You were spending a lot of time on the separation time, and which you found out that the separation time can be influenced by an order of magnitude higher than the dispersion itself. The description of the phase separation and the development of a modification of the Henschke model, which will bring this phenomena a real step forward. You have published 8 papers as a first author and co-authored 11 articles in high-ranked journals. And the topics were related to 5 fields. So microemulsion, Pickering emulsions, drop size distribution, rheological characterizations, and catalytic reactions. So all topics are very fundamental in the mixing, in terms of mixing. If you look at the process itself, if you look at the intensification on reaction of fluids within fluids. Additionally, you have managed and organized a workshop for PhD students, and you have shown your ability to not only work in as a scientist, but also on with people. So you have organized the workshop for PhD students with topic mixing meets reality. So there, also for that, thank you for your benefit and your efforts in this mixing group. For the next candidate, it was completely different topic. So Francesca Maluta, thank you for being here as well. This was a CFD study, and what I personally was overwhelmed was also one of the criteria, so that it has a very big impact to the industrial, to the industry. And your modeling of multiphase steered bioreactors focuses one of the megatrends which we have at present. Bioreactors are upcoming in all sorts of processes. And you prove that you're not only working in Italy, but also you went to the University of Alberta with Susan Cresta. You have the Huntsman International, were supported by Huntsman International in finalizing a project of development and validation of mechanistic models to optimize polyurethane and prove durability to have the industrial focus, which I evaluate very much. During the PhD project, you have gained solid skills in modeling complex and unresolved mixing problems, with particular attention into industrial multiphase systems and bioreactors. And there you have created the new mixing models for heterogeneous bioreactors. With your excellent skills in fluid mechanics and multiphase flow models, you have also a very clear and precise and easy. It is easy to follow your thoughts, and as I mentioned, the interactions between mixing and bioreactors are crucial. You have a personality and kindness, and you are appreciated in the group of mixing, in our group of mixing. So I'm very happy to have the honor for you both to present and hand over the certificate for the Young Researcher Award in Mixing in 2021.
Yes, thank you a lot.
Thank you.
So I would give you, Lena, the floor for your presentation.
Okay. Yes, I will just share my screen. And yes, today, for all the people who might not know me yet, of course, I would like to present a little bit what I'm doing. Some parts have already been explained a little bit. So I'm generally working in liquid multiphase systems, and especially on the impact of additives on dispersion and coalescence in stir tank. And I'm doing so at the Department of Chemical and Process Engineering of Professor Kraume in Berlin. I have a very short agenda here. First, I would like to briefly introduce what I did in my PhD thesis, then talk about some questions that I started to have and were not able to answer maybe during the time, and which currently led to which then led to my current activities and what I'm planning to do in the future in the fields of mixing. So in my PhD thesis, I analyzed dispersion and coalescence in liquid three-phase systems with surfactants. And this is a very specific topic, since usually you maybe have two liquid phases and a gas phase or a solid phase. But I didn't meet a lot of people who worked with three liquids in one system, or three liquid phases. The general aim of the whole project was to enable an efficient reaction of long-chained organic components in a biphasic system. For example, this can be the hydroformylation of olefins, but also other reactions are possible. And this should have been performed, or we plan to perform this in a continuous process where we have a reactor and a separator. And of course, we want a high interfacial area between the phases in the reactor, and then we want to reduce this interfacial area to recycle the second phase, which in our case was water. And also this phase contained the catalyst and the additives that we had in our system. And in the end, we hopefully get a very pure organic product phase. So the challenge, which is not really new, but also occurred in this context, is the optimization of the reaction and the separation step, so the overall process can work. And one of our solutions was to use non-ionic surfactants as an additive. And of course, you can imagine if you put 8 to 10% of surfactant into your system, then you will definitely get a high interfacial area, since you stabilize the emulsions and you get smaller droplet sizes. So in the reactor, that works perfectly, but it leads to problems with the phase separation. And this means we had to deal with the second process step here. And what we did is we used the system-specific phase behavior of these water-oil surfactant systems because it severely affects the coalescence in these systems. And this is just shown very schematically here. So if you have a water-oil non-ionic surfactant systems, the phase behavior is a function of the temperature and the mass fraction of surfactant in your system if you keep the oil-water ratio constant. So you get one phase, two phases, or three phases, depending on these two parameters. And the surfactant which you have is usually soluble in the aqueous phase at low temperatures and in the organic phase at high temperatures. And then there's this intermediate temperature range where the solubility is quite equal in both of these phases. And then what happens is that there's a third thermodynamically stable phase which is formed. And this is called a microemulsion or middle phase. But it's actually just one phase, just like the others. You can determine its density and viscosity. You can determine the interfacial tensions between the different phases. And this middle phase will also form droplets which break and coalesce. Another thing is that the catalyst always follows the surfactant, as you can see with the red dots that I showed here in this graph. And this is why we can perform the reaction, for example, at high temperatures, around 95 degrees or 100 degrees. And then our catalyst is in really close contact with our organic EDAC phase and will be directly converted to the product. Furthermore, for the phase separation, we need to change the temperature to some degrees, and then you will be in the middle of this three-phase area. So the third liquid phase is formed, and this really has a huge effect on the separation time, for example, in the decanter or just in a stirred batch tank if you stop the stirring. And this is shown here, for example, for this substance system, the phase separation time is around 81, is at a minimum at around 81 degrees. But if you change the temperature slightly, or even if you go, for example, to 70 or 60 degrees, then the separation time can take days, months, whatever. It's really extreme what is going on there. And this is especially interesting since in all cases we have an ultra low interfacial tension, since we have 8 or 10 mass% of surfactant in our system. And so the impact of the phase behavior is on the phase behavior is quite relevant. What I did in my thesis on a very fundamental level is to just analyze in a stirred tank what happens if we have a liquid three-phase system. And if we steer the system, what kind of droplets do we have? What kind of emulsion does occur? And how does the phase separation then work afterwards in a second process step if we, for example, just turn off the stirrer? And for this, the methods that I used are, on the first look, quite simple. So we have a stirred tank, just a batch, and we can analyze the droplet sizes with an endoscope in situ. This is shown here just for a very simple oil and water emulsion, so for a common two-phase system. And we can use an external camera to determine the phase separation process over time. So we get an information about the sedimentation and coalescence curve, and maybe also about the dense packed zones which occur in our system. Of course, we also analyzed the physical properties, and this was actually quite a lot of work, especially in the three-phase conditions, because there are a lot of things that we needed to learn just to be able to really get the measurements right. So when you go from two-phase to three-phase system, there's several things that can happen and which make it really interesting. So since you have three liquid phases, each of these phases can become the continuous phase depending on the composition and the process conditions. Furthermore, you can have either single droplets, I always call it. Of course, there are actually two droplet forms and two distinct droplet populations in your system. Or you can have multiple emulsions where one phase surrounds droplets of the other phase, which of course then changes the droplet size and also the phase separation behavior. And a lot of these effects that you have are quite similar in a way to two-phase systems, but there are a lot of details that you need to understand if you want to understand what is going on in the three-phase systems. And of course, I can't explain them in detail today. But the basic questions that we tackled were when does which emulsion type occur and why? And this was actually one of the major questions that we answered. And of course, we also looked at how this affects the drop size distribution, how it affects phase separation, and if there are ways to predict what is going to happen, either qualitatively or with models such as population balance equations or phase separation models. And the first question, when does which emulsion occur and why, is a very complex interplay between the different interfacial tensions that you have in the systems and their ratio, the temperature, the solubilities, and the overall process conditions. But we managed to now get a very good understanding on, and we can get a good prediction what will happen under which conditions. So I just showed today some very exemplary results in a model system that we used. That was a very short surfactant, which was very good, or was easy to measure in comparison. And you can see images of this system here. And this is one of the cases where we had a multiple emulsion in an organic continuous phase. And what we can do from these images, we can either analyze the overall drop size distribution by just counting all of the droplets that we see in the images, which is the red line here. Or we can distinguish between, for example, the outer droplets, which are the middle phase droplets, and the inner droplets, which are aqueous phase. So we get an information about either the whole system or about the two distinct droplet populations. If we change, for example, the process parameters a little bit, it can also happen that we get something like this. So we have an inversion. We have a different type of multiple emulsion, but here in an aqueous system. And you can also see here that it is possible to distinguish between the two phases because they have a very different appearance. So the inner droplets are quite clear and dark, and the outer droplets are a little bit more turbid. I think what you can also imagine is that the phase separation behavior in these two systems will be very different. For example, also again, very schematically shown here, such an emulsion in the upper example will separate like this. So we have very large multiple emulsion droplets in comparison to all the residual single droplets, which also occur in this system. And that means that these gray interface, the middle phase, will be formed quite fast, and the former inner droplets will be expelled into this completely coalesced middle phase. So we get a dense packed zone, and in the end, we also get several dense packed zones in the systems which overlap. And if we change the emulsion type, of course, this behavior will change a lot. So to get to this point, actually, it took us quite a while because we had to analyze all the physical properties, understand what we see on the pictures, and of course, not all of the pictures did look quite nice as they do here. But you can also see this behavior in the phase separation. So this is a little bit accelerated, but you can see that the middle interface is formed quite fast, and then you have a dense packed zone which is formed until the aqueous interface also comes to a rest. And what we actually got, and which is one of the main accomplishments, I would say, is that these phase separation experiments can be used as key experiments for the whole process development. So this phase separation experiments can be performed in any lab. If you have a double-walled glass beaker and maybe a thermostat and the specific components, you can just try how the phase separation looks. And this experiments, if you have a little bit of knowledge, you can use to determine the initial type of dispersion that you had. And for that, you don't even need the endoscope or the physical properties of the system, because the phase separation will show you what kind of dispersion you had, because it will change the direction and how the phases are developed. If you compare different phase separation experiments, you can also, of course, also get the idea about the drop sizes, if they will get smaller, larger, and you can even distinguish if there are multiple emulsions in your system or if they are just these single droplet populations. So that was one of the things that we could use for process development, because you can also perform these experiments in a more complex system, for example, with catalysts and also with some educts or side products in it, and they will give you the same information. So during that time, there were already a lot of questions that I started to have and which I was not able to answer in my PhD thesis, and some of them I will just show here. So one of was why do systems with actually quite similar properties coalesce so differently? And a colleague of mine at another conference recently said that the interfacial tension is irrelevant. And he was also working in a way with three-phase systems, and I tended to agree. Although I would say maybe the interfacial tension is not always as helpful as you might think. It's not irrelevant, but usually sometimes it just doesn't help you a lot. So there are a lot of additional parameters that we need to describe the interface, and therefore, for example, the coalescence behavior, such as the mobility of the interface, the rigidity, so it's resistance against deformation, the zeta potential. There are a lot of studies who also try to investigate this in more detail. Another thing that I started to answer is to question is how many experiments are actually reasonable. So during my work, we also evaluated how population balance equations can be used to predict the drop sizes and the phase separation models. And they can work in a small process window, and it's very interesting to work with these. But there are sometimes so many experiments that you need to do that if you know that you have a key experiment, which will basically give you the result of the phase separation, it puts into question if you would really do that on a realistic level. And I think this is a question that is also very important in less complex systems, for example, in simple two-phase systems with additives that I want to investigate in the future. And of course, we also analyzed the accuracy of these modeling approaches under less complicated conditions than the three-phase systems. And I think all of you will know that there are a lot of things still to do, and their specific models are always good at predicting something, but if you change the wrong parameter, they might give not so good results. So this is another question that I would like to investigate further in the future. So this leads me to my current activities, and actually I'm staying in this dispersion and coalescence and steer tank topic, but I want to expand it to liquid multiphase systems with and without additives. And these are basically two-phase systems in many cases. And what we can do at our department is the nice thing that we have very different measurement techniques, mostly optical techniques, which we can use to analyze droplets forms, single particles, and also interfaces. And I would like to use this reduction of complexity for model elaboration in the future in very different substance systems. So my current working group consists of a few PhD students and of course a lot of bachelor and master students, and we are working in liquid two-phase system, mainly without additives, with surfactants, with nanoparticles, and with proteins or enzymes as additives. And today I would like to briefly talk about the nanoparticles, because there are some nice similarities, but also differences to the surfactants that I presented before. Because nanoparticles can also go to the liquid-liquid interface and stabilize emulsions against coalescence. But they do so not by reducing, for example, the interfacial tension, which usually stays constant or nearly constant, but they do so by forming a mechanical barrier that leads to, that prevents the deformation of the droplets and thereby also the coalescence. And the nanoparticles also come in very different sizes and shapes and with different surface modifications. So these are very interesting additives at interfaces. And the kind of experiments that we are focusing on, for example, now are these. For example, we first start with a simple water-oil system, here indicate water, which is the yellow curve. And we measure the Sauter mean diameter over time. At 0 seconds, the stirrer is started in our stir tank. And at 1,200 seconds, there's a step in the stirrer speed. So there's a different energy dissipation rate, which leads to another coalescence behavior. And each of the data points here represents actually one distribution, which is formed by, for example, taking 100 images with 500 to 2,000 droplets. So there's a distribution behind each of these data points. And if we add nanoparticles to our systems, for example, here up to 1 weight% in relation to the dispersed phase, then we see a huge impact on the coalescence behavior. So the coalescence is inhibited by the presence of nanoparticles in these systems. And one of the current projects is to use, for example, population balance equations, such as the model by Koulalulu and Tavlaridis that I think many of you will know, and to modify it to account for the presence of nanoparticles in these systems. And there are several ideas that we have. The first one that we implemented was to change the coalescence efficiency according to the coverage with nanoparticles. So if you have two droplets which are partly or completely covered with nanoparticles, and these two intend to coalesce, then of course a new droplet is formed with another small overall interface. And this means that some of the nanoparticles need to be expelled from the interface, or there needs to be a multi-layer of nanoparticles at the interface. And there's a certain desorption energy, which is much higher, for example, in comparison to surfactants. And this energy needs to overcome, and is kind of the energy barrier that prevents coalescence if you have a high coverage with nanoparticles. So that was just one basic idea, and we modified the Koulalulu and Tavlaridis model, and the results that we had here are shown as the lines in the curve in the diagram, and we get a quite good description, not perfect yet, but of the both the Sauter mean diameters in steady state and also of the step experiments. And another thing which I think is very important is that we not only try to fit the Sauter mean diameters with our model, or to predict it accordingly, but also the whole distribution of the system. And the experimental distributions and the modeling results are shown here. And you can see, although the experiments, of course, deviate a little bit or scatter, we get a quite good description of how the distribution width broadens and how it's switched or shifted towards larger diameters. So this is actually quite promising. Of course, there are a lot of things that we can still improve. For example, apart from the coverage, we also want to introduce a physical parameter of the interfacial rigidity. And this means that we measure, for example, the dilatational viscoelasticity of the interface in the tensiometer as a function of the coverage or the particle mass fraction. This can also give you some information about multi-layers that will occur and can be maybe in the future introduced also into this model to optimize it further. And of course, we have 100 other ideas. For example, the nanoparticles change the viscosity of the phase they are in and make it shear thinning, sometimes even viscoelastic. So there are a lot of things to do that, we are currently working on. And for everyone who's interested in details, I will also be at the ECCE conference in September, and we'll present a little bit about the model that we developed here. So with that, I would just come to a brief outlook. So I already showed you what I'm planning to do during the next years in my research. And I also started what I call a little side project. And you know, little side projects can sometimes take a lot of time too. And since we all like optical image analysis, at our department, and I think Professor Kraume will also show some nice pictures and videos later. So we did some preliminary pictures of my little side project, which looks like this. So, and if you're trying to figure out where the droplets are, this is the image of my first child. My son will be born in October, I hope. And with that, I would like to really thank you again, the award committee, for giving me this award, also at a very perfect timing where I'm thinking a lot about how I can combine these two projects in the future. And it gives me really a huge motivation that I got this award and that I also was invited to be a guest member of the mixing community. So thank you very much for that, and also for your attention. And congratulations to Francesco. I'm really happy to share this award that we both can present today. Thank you very much.
Very good. Thank you, Lena. And first of all, congratulations to your side project, which is really fantastic. And I'm happy that you're so proud and well prepared for everything which is coming up. So so I'm very happy for you. So, but coming back to to the presentation you had, I think there are quite some questions because it's a very fantastic topic you have presented here. To start with, I would like to ask you the main differences in separation when you look at swarms compared to single droplets.
Yeah, that depends if you want swarms of 2 liquid phases in systems with 2 liquid phases and 3 liquid phases, of course. With the 3 liquid phases, it definitely is this complication that you have the 2 different populations which interact with each other. I mean, everyone here, I think, knows that you have a single droplet which will sediment. And if you have a swarm, there are a lot of interactions which will happen. And this is especially tricky when it comes to the 3-phase system, since you have this overlapping dense packed zones. And I think it's also, we did some modeling of this, but to really describe how the dense packed zones overlap, that's a little bit utopic, I think. I don't know if we will be able to do that in the future.
While looking at the pictures, I was thinking of it would be beneficial to change temperatures while during the separation process in order to accelerate some of the days or weeks of waiting. If you have smaller temperatures, with your example, there was 60 degrees, or 70 degrees. So if you're there, it would be beneficial to heat up the 10 degrees in order to accelerate the separation time.
Mm-hmm. Yeah, that actually is also the thing. So we have some project partners which do really control the mini plant that was built, and which is actually a continuous process. And unfortunately, this fish that I showed here, it's not always like this well fed. It's sometimes really thin, and the range where you can go with this 3-phase system, it's maybe 1 or 2 degrees, and then again the separation time becomes much larger. So yeah, the minimum depends, of course, on the composition of the system. So the one that I showed here is a specific water-oil ratio on surfactant concentration, and you have this 81 degrees minimum. And it's a certain emulsion type. I can't say which one. Let's say it's an organic continuous phase with multiple emulsions, for example. And if you slightly change also the composition, then your temperature range will also vary a little bit, or also phase separation time will be affected since the overall separation process is different. I think what you need to consider is you definitely need to find this optimum with some key experiments that you do, for example, over temperature and with 3 or 4 different compositions. And then you can also see, for example, if you have a, wait, I will just go a little bit further. If you have a system that coalesces like this, then this means that if all the droplets sediment away from the upper height of your emulsion, so the organic phase is usually our product that we want to have, and it's always beneficial to have this organic phase as the continuous phase if the phase separation works in a reasonable time scale, because then it's simple to just have the outlet of your decanter here somewhere at the top, and then you actually don't mind that there's a dense packed zone forming in the bottom. You can just recycle out of that. But if you have another type of reaction, for example, where the aqueous phase is your product phase, then you need maybe to switch the emulsion type, so you get a good clear phase at the outlet at the bottom.
May I ask a question?
Yeah, sure. Yeah, go ahead, Alvin.
Yeah. Lena, it was a splendid talk, very well put together, very, very difficult topic. And I liked your first question that you posed after you described the actual PhD about why do these things behave differently, because it's even well known, interestingly enough, I think Rushton of Rushton turbine fame first observed that the separation of oil and water was different depending on which was the continuous phase. Mm-hmm. So just with a pure water oil system, they separate quite distinctly different rates. If my memory serves me correctly, when the water is dispersed, it separates more quickly than vice versa.
Yeah, I think that's true. Yeah.
But have you got an explanation even for something as simple as that?
Now, actually, I have one of our PhD students exactly investigating this in a batch tank, and we are putting together a paper because we did not only analyze the phase inversion, and I agree that it's crazy how much it can change. Also, there's an effect of temperature where the oil and water or the water and oil emulsion reacts quite differently. And this is, yeah, one of the things that still baffle me, because if there would be any additives in the system, I could maybe explain it better, but in pure water, oil and oil water, it's crazy how much it's affected.
Right.
And I presented that at another conference in March this year, and I also get maybe some hints that maybe also the different phases will maybe coalesce more with the walls of the tank or something like that, but nobody there really offered an explanation. So afterwards, I thought, okay, so maybe I'm just not stupid. Nobody really knows why.
No, I don't think they do. I'm sure you're not stupid, but it's very, very curious. Yeah. Thank you very much. Very nice.
Yeah, another question maybe. So oil and water systems do behave Newtonian, and at Berlin, you're always looking at non-Newtonian fluids. So what would you expect in with that kind of behavior in non-Newtonian fluids? Okay,
maybe first for the three-phase system, that is actually one thing that was really nice. Phases are Newtonian. Even the middle phase is a Newtonian, it does have a Newtonian behavior. So that's one advantage of this. But for example, when it comes to the nanoparticle systems, I mentioned that before, that the one of the phases will be partly shear thinning, for example, or even viscoelastic. And I know how this difficult this topic is, since a lot of colleagues work on that. We are actually trying to yeah, there's several things how you can address that if you look to additives, for example. So if you say, okay, we don't have so many nanoparticles in our systems, most of the nanoparticles will be at the interface, then maybe the phase where they initially are dispersed is more or less Newtonian, but the interface itself will become, for example, viscoelastic. So that will definitely complicate things. And we are also doing some experiments for single droplet analysis, so rising or falling droplets. And you can analyze the fluid dynamics in very different systems, also with different viscosities. And of course, this dramatically changes how they, for example, sediment. So sometimes they oscillate, sometimes they are very, yeah, going very straight forward or just straight down. And I think there are not so many modeling approaches really including this yet. What I'm currently working on was just, again, the pure water oil systems, where we just changed the dispersed phase viscosity, because this is something that in the, for example, in the Kulalulu and Tavlarides model for population balances is not included. And there are different approaches, and for example, by Allopeus. And we actually want to use our very detailed experiments that I showed over time to analyze this a bit further.
Lena, thank you. It was really a pleasure having this talk, and I could imagine with all the questions we could talk on for hours. Yeah. We need to have the time, the timing, and thank you again for this wonderful talk. And I'm looking here in the panel, and I would now give Francesco Maluta the floor to present his PhD thesis.
Okay, here I am. Can you see it?
Yes.
Okay.
Very good. So go on.
Okay, thank you very much for your introduction. So today I will be presenting a presentation titled CFD Predictions of Gas Cavities, Power Consumption and Flow Regimes in Aerated Bioreactors. So in this presentation, I'll first talk about the reasons why such a study is relevant. I'll go through the latest results we've obtained in the simulation of aerated fermenters. And finally, I'll show some of the open questions, some of the challenges that we are facing right now. So I'm sure that here everyone knows the potentials of CFD as a tool for system-specific scale-up and design, and the importance of aerated stirred fermenters in industry. We actually saw a very interesting presentation yesterday on the topic. So the main advantage of CFD is that in principle, we can obtain local and instantaneous information on the flow field, on the species concentration distribution, and of course, on the interface mass transfer. So giving a little bit more details, we focus our attention on Rushton turbines. Since they are still industrially relevant, they've been extensively characterized from both a numerical and experimental point of view, and because the prediction of the formation of the aerated cavities behind their flat blades is a challenge from a computational perspective. So we are aware that other types of impeller exist, better suited for gas-liquid dispersion. And in fact, we plan to extend the fermenter analysis to tanks steered with different impellers, and experiments are actually currently underway. So in this presentation, I'll focus on two different lab-scale stirred tank configurations shown here. So we studied a 4-stage, flat-bottom, fully baffled tank steered by 4 Rushtons, and the other configuration corresponds to just the lowest stage of this Hohl fermenter. So in the last, let's say, year and a half, we managed to predict the formation of the cavities behind the blades of the Rushton turbines in different operative conditions. We validated the cavity shape and size predicted by the CFD with some experimental data. And the proposed approach managed to predict the power draw reduction due to the formation of the cavities. And we gain insights on the power reduction mechanism, analyzing the local pressure field in the impeller zone. So with the proposed method, we can predict even the flow regime transitions and obtain the gas-liquid flow field in different flow regimes. So going a little bit more in depth, I'm going to present the CFD model adopted for the simulation of aerated fermenters. So the computational model is based on the steady state, incompressible, isothermal, Reynolds average, Navier-Stokes equations extended to multiple fluids through the two-fluid model. The Reynolds stress was a model with a K epsilon model with phase average properties. And here on the right-hand side of the momentum balance equation, there are two terms representing the interface momentum exchange, namely the interface drag force and the turbulent dispersion force. The drag force was expressed in terms of the bubble terminal velocity only, as previously proposed by our colleagues in Palermo. And the turbulent dispersion force was modeled with the Burns model. We studied the interaction of the interface forces, and we concluded that both the continuous and the dispersed volume fractions must be included in the formulation of the forces, and actually their balance allows the formation of aerated cavities behind the blades of the impeller. So as we were saying, the interface forces depend only on the bubble terminal velocity, and the Grace model was adopted since it can describe the motion of spherical and ellipsoidal bubbles. A single terminal velocity was adopted, meaning that a monodistributed bubble size was assumed. In order to attain the bubble size, the correlations developed by Alves for systems with a single impeller were adopted, which are shown here in the green tile. The average south terminal diameter in the impeller zone can be calculated knowing the superficial gas velocity and the gas power consumption of the impeller. And to obtain the gas power consumption, we use the correlations developed by Smith, shown here. Assuming a single bubble diameter, of course, is not the only viable approach. Many research groups successfully adopted the population balance to get the bubble size distribution, in fact. So we adopted a single bubble diameter to cut down computational costs, allowing the adoption of the proposed model to industrial size fermenter. Moreover, we have to say that few studies address coupling between CFD and population balance equation in stirred tanks at high gas flow rates, And especially, let me stress this, when the segregation occurs, so when we have the cavities. Okay, the first set of results that I'm showing concerns the prediction of aerated cavities behind the impeller blades. On the left side here, you can see the results of the tank operating in the conditions shown here at the top of the slide. In the 4 impellers, the cells with a gas volume fraction higher than 0.95 have been marked to highlight the cavities. In this condition, cavity develop on each of the 4 impellers, but behind the blades of the lowest impeller, the cavities are considerably larger than in the other impellers. This is due to the fact that the air sparger is positioned just below this impeller, that therefore treats the larger gas flow rate. Increasing the impeller rotational speed results in the disappearance of the cavities behind the blades of the upper impellers, and gas volume fraction higher than 0.95 are found just behind the blades of the lowest impeller. Moreover, these cavities, as you can see, are smaller than those obtained in the conditions on the left side. So the model allows to predict the different gas accumulation observed in different operative conditions, as well as the difference between impellers positioned at different heights. Once we managed to predict the aerated cavities, we used the single impeller stirred tank to quantitatively validate the results. Adopting the correlations developed by the group of John Smith, we identified 4 conditions in which vortex clinging and small fifth cavities were expected. As you can see here from the pictures, in case 1 and 2, the clinging cavities are predicted, as expected from the correlation. The color map indicates the gas volume fraction, and once again, just the cells with a gas volume fraction higher than 0.95 are displayed here. The other 2 cases, case 3 and 4, show the small 3-3 cavities, and it is evident the alternating pattern between clinging and large cavities. Afterwards, we compared the area of the cavities as obtained from the simulations and from experimental data previously collected in our research group. To determine the gas-liquid interface, 2 thresholds were adopted, the lowest corresponding to a gas volume fraction of 0.95 and the highest being 0.99. And the numerical results are in, let's say, very good agreement with the experiment. The correct prediction of the aerated cavity size and shape is important since the power drawn by the impeller decreases as the accumulation of the gas behind the blades increases. So in the picture here on the right, the gas to ungas power ratio is shown as a function of the gas flow number. And in the figures, there are relative power demands measured with a torque meter, and the relative power demands as obtained from the simulations calculated as either the total torque on the moving walls or as the mass integral of the turbulent dissipation rate. So from this plot, we can see that the experimental and numerical data are, let's say, in fair agreement, and that the turbulent dissipation rate is correctly predicted by the simulations. To study the power reduction mechanism, we analyzed the pressure field in the impeller zone. So for a quantitative analysis, we defined 2 sets of probes on 2 opposing blades, and you can see them as yellow spheres. 2 probes laid inside the cavities, either clinging or large, and the others were in front of the blades. In the plots, you can see the non-dimensional pressure as registered by the probes. The probes positioned in the trailing position of the blade showed a sharp reduction of the pressure. And then when the probe was completely surrounded by gas, the pressure values reached a plateau. The behavior of the probes in the leading position of the blades depend on the cavity size of the preceding blade. In fact, the pressure measured by the probe following a clinging cavity remains almost constant and close to the value measured in single phase, whereas the pressure measured by the probe following large cavity substantially decreases with respect to the other probe. As we know, the presence of large cavities reduces the amount of liquid in the space between 2 consecutive blades, thus reducing the amount of pumped liquid and thus diminishing the resistance faced by the blade that in turn draws less power from the shaft. The power reduction mechanism was already described by Middleton and Smith, and these results quantitatively confirm the power reduction mechanism previously described. The cavity size and shape were validated in just one gas liquid flow regime, namely the loading regime. So using the correlations developed by Professor Alvin Nienow, we selected 4 different operative conditions corresponding to the complete recirculation, loading, and flooding regime. The pairs of impeller rotational speed and gas flow rates are reported here in the table, and clinging cavities are expected in case 2, and 3-3 cavities are expected in case 3. So in the maps here, they are obtained on a vertical plane for each of the 4 cases, and the cavities are highlighted with a pink surface. The fixed length vectors show the liquid circulation pattern, and the color code represents the gas phase volume fraction. The simulations satisfactorily predict the expected flow regimes. In particular, gas is almost homogeneously dispersed in a complete recirculation regime. In the loading regimes, the gas phase is distributed mostly above the plane of the impeller, and in the flooding regime, it is evident that the impeller fails in distributing the lighter phase that travels almost undisturbed from the sparger to the upper surface. The mean age theory developed by Lena and Tilton was extended to 2-phase systems, and the analysis was performed in the 4 different flow regimes presented before. So we show the gas mean age in terms of local gas mean age divided by the mean residence time in the tank. And in complete recirculation regime, although the gas phase is almost homogeneously dispersed in the tank, we can see that the age of the gas below the plane of the impeller reaches values up to almost 2 times the mean residence time, and therefore the expected mass transfer driving force may be lowered with respect to the upper zone. In the loading regime, radial mean age gradients become important, and the age of the gas entrained in the lower recirculation loops is much higher than in the rest of the tank. In the flooding conditions, the gas travels almost unaffected by the impeller, and the axial gradients are observable. So the results I've just presented are obtained with a single bubble diameter. With this simplified approach, we managed to predict many features of aerated stirred tanks, but the main drawback of this approach is that it may not be acceptable to predict the interface mass transfer, and in particular the specific interfacial area. So in fact, in stirred tanks, the interface mass flux is commonly modeled with this expression, where N is the molar flux. According to the widely used Eddy-Cell model by Lamont and Scott, this expression is used to model the liquid side mass transfer coefficient. KL depends on the local turbulent dissipation rate, and therefore we can predict it since we've seen that the average epsilon field produces power numbers close to the experimental values. The next term to model to obtain the interface mass flux is the specific interfacial area. So far, in the context of the 2-fluid model, we used a simplified expression to obtain it at a high gas volume fraction and where there is segregation of the 2 phases. A more realistic strategy would require to model the bubble size distribution with a population balance approach, as already done by other research group for dispersed gas liquid systems. And we are currently investigating this path, and in a few slides, I'll show some of the open issues we are facing. The last term to model to obtain the interface mass flux is the driving force of the process. So once the turbulent 2-phase flow field is satisfactorily predicted, the species distribution inside each phase is governed by a scalar transport equation. One way to validate the transport dynamics is to compare the numerical and experimental mixing times following the injection of a tracer. And such experiments are currently underway in our labs. Okay, so in the last 5 minutes of my presentation, I'm going to show the modeling and numerical challenges that we are facing right now. So basically, we are struggling in obtaining a realistic prediction of the specific interfacial area with a population balance approach in aerated stirred tanks with a high gas holdup. The first critical choice to be made concerns the selection of the appropriate breakup and coalescence kernels. And to address this point, we use the same kernels proposed by our colleagues at the Politecnico in Torino. in the simulation of a similar system. Concerning the accurate description of the flow field in the impeller zone, one of the main challenges to face is the modeling of the turbulence where segregation of the two phases takes place. Adopting a RANS approach, a simplified description of the turbulence entails determining the turbulent variables, adopting either mass average properties, the properties of just the continuous phase, or describing the turbulence in each of the two phases. So this is especially important where aerated cavities develop. The description of the flow field in impeller zone is important since here the turbulence is order of magnitude higher than in the bulk. In a previous study in very dilute conditions, we observed that because of the high turbulence, the breakup events mostly occur in the portion of the volume swept by the impeller, as you can see here in the contour plot. Another challenge is the accurate description of the impeller zone from an experimental point of view. In fact, accessing the zone is often very difficult. And even the correlations developed by Alves to obtain the average diameter in the impeller actually measure the bubble size at some distance from the impeller zone. And at high gas volume fraction, breakup and coalescence may change the bubble size distribution, making the collected data not fully representative of the bubbles distribution in the impeller zone. The last aspect that I'm showing concerns the spatial discretization of the impeller zone. So these two contour maps show the gas volume fraction distribution, and the results are shown on an horizontal plane passing through the center of the impeller. Two identical meshes were adopted, the only difference being in the number of cells in the volume swept by the impeller. In particular, the results on the left are obtained with a finer impeller discretization, and these data better agree with the results obtained with a much finer grid. It is worth observing that the largest differences between these two contour maps are observable in the bulk of the tank, where the spatial discretization is actually identical. So this means that the description of the impeller zone has a large effect on the whole domain and not just in the close proximity of the turbine. Okay, so calculating the bubble size distribution with the population balance equation solved with the quadrature method of moments, we observed that the southern mean diameter in the bulk of the tank, predicted by the simulations, fairly agrees with that from established correlations. On the other hand, the prediction in the impeller zone did not agree that much, as you can see from the plot here. This may suggest that at high gas volume fraction and where there is segregation of the phases, the population balance struggles to predict the size distribution close to the impeller. Another aspect that deserves attention is the choice of the bubble diameter exiting the air sparger. Different correlation exists in the literature, and as you can see, while the diameter of the bubbles exiting the sparger weakly affect the southern mean diameter in the bulk of the tank, it has a large impact on the predicted southern mean diameter in the impeller zone. The last issue that I'm showing today is related to the numerical problems in the impeller zone. Since we are pushing the limits of the Euler-Euler model, we've observed that when the segregation between the phases occurs, the typically adopted steady-state solver diverged. We managed to get robust and reliable results by adopting a pseudo-transient solver, which is still a steady-state solver, but it adopts implicit relaxation of the equations. Nonetheless, the pseudo time step must be lower when the segregation starts. Talking about the impeller zone, we've seen that adopting fine grids that give grid-independent turbulent variables produces some disturbances at the interface between the moving and stationary zone when the multiple reference frame is adopted. Okay, so to sum up, with this presentation, I've showed that we can predict the flow field of aerated stereo fermenters in a wide range of operative conditions. We validate the formulation of cavities, shape and size, power consumption, and the flow fields in Stinger tanks operated with Rushton turbines. We will extend the study to other types of impellers and tank scales, and several modeling and numerical aspects need to be addressed to accurately predict the turbulent flow field and the bubble size distribution in the impeller zone, and allowing for the realistic prediction of interface mass transfer. Let me conclude by thanking the European Federation of Chemical Engineering and its working party on mixing. Thanks to Brucato for sponsoring the award. I want to thank our research group of the University of Bologna. Congratulations to Lena for the award, but especially for her side project. Thank you very much for your attention.
Yeah, thank you, Francesco, for this wonderful talk. Yeah, as you mentioned, Russian turbines are still used in a wide range of industrial processes, and therefore starting with the research and the CFD modeling with Russian turbines is a very good step. And you have very well described all the cavities which arouse directly behind the blade. And before starting and evaluating other types of agitators, what would you expect with more modern types or more recently developed agitator types when you would analyze those?
It depends on the impeller, of course. So right now in our labs, we are doing experiments in a 4-stage lab scale fermenter, and the lower impeller will be actually a BT6. So we hope that the formation of the cavity will be reduced. And of course, if we don't have cavities, from a computational point of view, it will be easier for us. So let's say this is our preliminary knowledge on the topic. And then again, it depends on the impeller, right? So as long as we can validate our simulation with the experiments, I guess we can extend this study to other types of impellers.
Okay, there are quite some additional questions. So if you look at the Russian turbine itself, so at the geometry, there is quite some turbulence right coming from the blade itself. So if the fluid is streaming out of the horizontal blade, here are some questions in terms of cavities. Stuart Stokes, I will just read it. Prediction is quite good. The visual imply you do not simulate perfectly the experimental system. Did you simplify hub geometry, blade or disc thickness, real vessel, disc shape, and so on? Could it be the prediction would be even better if these details are included?
Okay, so concerning the simplifications, we treated the baffles and the blades of the turbines as like surfaces without any thickness. So yeah, this is correct. Concerning the effect on the results, I'm not so sure of that. I mean, in a single phase and dispersed regime, we've seen that this has very little impact on the results. So maybe we can investigate that, but I would say that this is not a priority at the moment, and there are still other open issues that are way bigger than that, but we don't expect a very big difference by adopting a real fake blade.
Okay, then we have another question in with regard to simulation of the rotation of the impeller using different methods like sliding mesh and different turbulence models.
Again, so we want to use this model, we want to validate industrial systems, right? So we can, of course, change the way we model the rotation of the impeller. But if you use a sliding mesh, sliding grid approach, that means that we have to use a transient solver. We have to average our results over several rotations. And of course, this dilates the simulation time. So that's why we focused on the multiple reference frame approach. And I mean, the results compare kind of well with the experiments. So I guess that the interactions between the different models that we can use to model the rotation of the impeller, maybe they are not the fundamental. I mean, they do not change the basic idea of our results. So that's what I say. Concerning the turbulence model, there are open. It's one of the open questions that we have right now. So again, we use the K epsilon model because I would say that is the industrial standard. It's one of the most validated models, and it performed well in stirred tanks. So I would say that we want to focus our attention on the multi-phase extension of the models rather than choosing K epsilon, rather than K omega or Reynolds stress model. So there are, but it's an open question. So that's as much as I can say right now.
Yeah, very good. Thank you. Another question. One of the main aspects in modeling is always the validation of the model or with reality. And you have described very well the difficulties also in terms of the geometry. So what needs to be focused, where to put the focus on the mesh. Can you describe how the validation of the bubbles right behind the impeller, how you have yeah, validated those in your process?
Okay, so concerning the size of the cavities, I would say.
Exactly.
So yeah, there was a paper published a while ago where we actually okay, I wasn't there, so I'm not 100% sure, but we actually analyzed with the optical methods the cavities behind the impeller blades, and we just took the area. They are colored in different with different colors, right? So depending on the amount of gas. So that's how we extracted the experimental data, get the area of the cavity. And with the simulations, we actually saw that there was accumulation of gas. So we took two thresholds. So I mean, even from an experimental point of view, it's difficult to see where the cavity ends. Okay, so there is a kind of a tolerance, I would say.
Mm-hmm.
So
okay,
that's what we did.
You have specifically chosen one droplet diameter. So what would you expect if you change that diameter? Of course, it will have a significant impact on the time for the calculation, but what other effects could you get?
To answer your question, so changing the diameter of the particle, of the bubble, sorry, actually has a very big effect on the cavity. So what we are saying right now is that with the population balance, since there are troubles in the impeller zone, right? So the bubble size is too big and it doesn't allow for the formation of the cavities, or at least they do not compare that well with the experiment. So that's why we are focusing on impeller zone. That's why we feel the need to have more models, even more experimental data to validate that, because changing the diameter of the bubbles has a huge impact on the cavity size and hence the power consumption and flow field and then so on in a cascade, right? So
yeah. So one last question, because I'm looking at the time.
Sorry, I think that Professor Kraume has the hand raised, so I guess he has a question as well.
Wolfgang, it's up to you to decide.
Yeah, okay, then we have two, but one question. What would you expect in non-Newtonian systems, such as bioreactors, in the turbulent flow regime?
It's actually a very interesting question. So changing the rheology of the fluid would change the bubble size. That's the first thing that pops in my mind. So of course we have to investigate that. If I had a straight up answer, I would have published it already. So it needs a lot of study, especially from an experimental point of view. As you were saying before, we need validation. Otherwise, we cannot predict things in a very serious way, I would say. So it's actually one of the open issues that we have to.
So you're a young researcher, so
yeah, there's time.
There's time. So Matthias, so then I give you the last question.
Yeah, Francesco, congratulations for this impressive work on gas liquid flow. So I would like to go a step further. We've seen improvements of the Russian turbines for decades now, just trying to avoid this decrease in power consumption. So my question is, do you see a possibility to combine your simulations with an optimization of the stirrer geometry? So that would be really interesting, just to find a geometry where this drop of power does not, or power number does not exist any longer.
Sure. I mean, that requires foundings first. I mean, it would be a very interesting study to being able to change the little part of the geometry, maybe in an automated way, then perform simulations in batch and see at the end of the day which is the best fit. That would be interesting. I don't see any modeling problems with that, except with but I see some computational times problem, right? So that's the only drawback. But so if someone wants to fund me for this search, I'm up to it.
Okay, very well. Good final statement. And yeah, I will give the word to Alvin or to Juicy. I don't know who is taking over.
The floor is for Alvin and Ellen. I just want to introduce the sponsors and the acting chair that will present the Nienow Lifetime Recognition Awards.
Thank you, Jussi. So I'm honored and very pleased to be able to introduce this Nienow Lifetime Recognition Award, sponsored by my wife Helen and myself. And Helen's joined us just for a brief moment to acknowledge that too. So we'd like to thank the Working Party Committee for accepting our offer to sponsor the award in both our names. And it's largely because we've had such happy attendances at meetings and conferences, in my case since 1974, and it's enriched our lives, and we have made a lot of friends. I thought it'd be interesting just to go back a little bit about European mixing conferences, because there are some rather strange features in the background. So the first of the conferences was called Mixing and Centrifugal Separation. It was a financial venture run by BHR Group in the days when they started to run mixing conferences, but it was largely, like all the conferences at that time, a financial venture. And I was on the committee, but it was driven by Nick Coles, who was a bit of an entrepreneur, but certainly not an engineer or scientist. And I think he felt that since impellers rotated and centrifuges rotated and fluid in cyclones rotated, the two went together, which of course they don't. But that was the first conference. And as you can see, I've been involved now for approximately 47 years. There was then a brief period in which a critical point here is that the working party, our working party, was founded at a conference in Mons in Belgium, run by Professor Bruxemann, mixing in the chemical industry. And at this conference, the lead BHR group organizer stated that the conferences were now losing money and they wouldn't run anymore. Now, because the working party had been founded, Ivan Forst had been invited along as secretary of the working party. And from that point on, it moved away from BHR Group to the working party itself. But the BHR Group continued to publish the proceedings because, as you can see, they made a very nice job of it. So the first time it really became totally integrated into the European system was in 1988 in Pavia, the 381st event of the European Federation of Chemical Engineering, and so on and so on. It was chaired by Giancarlo Baldi and Franco Magelli, and there are a number of familiar names there who also became awardees. And here I've listed the awardees, and you'll notice there's a gap between that 1988 and the dates on this slide. As I recall, but I don't have the details, the arrival of an award came about because Pavel Dietl was chairman of the working party, and he got some funding from a company. I've been unable to find out who that company is. I remember it from the meeting, and John Smith was the first awardee. I know for myself, because I was the second awardee, and I was kindly sponsored by, or it was sponsored by Cato. I don't know about John Bourne and Ivan Forst, whether there was an award or not. I know there wasn't for Joelle, because I contacted him and he confirmed it. Then for 2 consecutive conferences, BHR Group came back in and sponsored the award, Franco and Harry, and Unilever sponsored the award when the conference was held last in Toulouse. And now we have 2 splendid award winners to take over the role, following on from what I think is a pretty impressive group of mixing specialists who've done a lot for the topic to make it both academically respectable as well as industrially very important. Here's a picture, a little bit like one Jussi showed early on, of the first 4 award winners from about 2007. And a fine looking bunch they were, and some are. So now we have Alberto Brucato and Matthias Kraume, 2 absolutely world-class chemical engineers, and it's interesting to trace their connections. So Alberto got in there first, but that was largely because he became an academic pretty early on, not as a professor, but he attended a conference in 1988, and that was, well, I know it's the conference paper. He may have gone earlier, but there's no record of a publication. And now he's a full distinguished professor in Palermo. In the case of Matthias, he spent 9 years in industry with BASF, and then did what is relative, well, it used to be relatively common. I'm a bit out of touch now, maybe it isn't, but he had a distinguished career with BASF, but he went to be a full professor straight away in Berlin and developed its own character under his guidance. And he first appeared at a conference in 1997. interestingly, I had a presentation at that conference that was directly related to the paper he published when he was at BSF. And it was a very important paper because what he showed, and we're now drifting on to his major research contributions, was that when you mix things, homogenize them in the presence of relatively concentrated suspensions, it takes a long time. And this can have serious consequences for all sorts of things going wrong, while any additives, for example, in crystallization or such like, for things to take place slowly and get to, for example, primary nucleation. Anyway, it was a very important paper. I talked about it, and Matthias was the first person to question my paper. I don't think he was rude, but anyway, he's always been impressive as a questioner at conferences and as an academic since he became an academic in Berlin. If we go on back to Alberto, of course, his big contribution has been applying computational fluid dynamics to stirred tank reactor mixing. He developed a thing called the inner-outer concept, and he's perhaps one of the most famous of all chemical engineers, because in CFD now, when there are solids in the system and the system is turbulent, there's the Brucato correction factor to allow for the enhanced turbulent drag on dispersed solids. And it's a standard procedure and commonly used. Another area he's worked in is the analysis of unbaffled vessels for a wide range of mixing applications. Unbaffled systems were sort of dismissed a long time ago, but he has opened up the topic again and shown all sorts of possibilities. And part of that has been integrating fluid mechanics and bioprocessing, especially in relation to animal cell culture. If we go to Matthias's other contributions, well, we heard a splendid talk earlier today from Lena, which was a development from a whole range of PhD studies coming out from Berlin on the topic of drop breakup and coalescence with surfactants and without surfactants. He's also, particularly in recent times, done a lot of work in, again, integrating the fluid mechanics and bioprocessing, in his case, especially with stem cells and mycelial fermentations, where the potential for mechanical stress causing problems is very high for a variety of reasons. And if we look at their other contributions, both have made major contributions to the community. Alberto was the co-chair of mixing in Bologna. He has been a strong supporter of the Working Party ever since he became an academic. He's a big supporter for Italian process engineering and indeed bioprocess engineering. And I think it was impressive that his award of the Lifetime Recognition Award was strongly supported by another well-known CFD expert. And he's quite an international figure and fairly flamboyant, as you can see in that photo. Now, Matthias has been, again, a strong supporter of the Working Party and of German process engineering, serving on a wide variety of committees. And in his case, somewhat unusually, but again, very impressively, he was strongly supported by Bayer and Ikato, by industry, which is pretty unusual for academics being proposed for this sort of prize. And again, a very well-known international figure, presented many, many talks at many, many conferences on a wide range of topics, I should add. Here we see our two winners enjoying themselves at Mixing 2012 in Warsaw. And now I invite them to give us what I'm sure will be splendid presentations, and congratulate both of them on behalf of myself and Helen on the Nienow Lifetime Recognition Award. Thank you. I'm not quite sure from the order who is meant to speak next, but I have finished, so I better see if I can get rid of my screen. Show? No. Help. Here we are. That's it. Over to you.
Thank you very much, Alvin. Congratulations to Matthias and Alberto. We can start now with the presentation of Matthias. The floor is yours.
Yeah, thanks, Giusy. Yeah, thank you so much. Hi, Helen. Nice to see you again.
Lovely to see you all. Yeah.
Thank you for the Nienow Lifetime Recognition Award. I think this is a wonderful possibility for the working group just to hand over these kind of awards. I even would prefer the Young Researcher Award, because those young researchers, they have their scientific life in front of them. Elderly people, well, they can have a look back. And anyway, so once again, thank you so much. When I heard for the first time that I would receive that award, I was thinking of the list of winners already shown by Alvin. And I had a little bit of feeling of a burden. Do I really deserve such an award? But that's not probably the most important issue. Others have decided to do so. And the second point was, now I'm getting really old. But that's the way it is. Anyway, so now I would like to start with my presentation. And I hope that you could see my screen now. And first, I would like to acknowledge my co-workers, Marcus Colano, Chan Chao, Alexander Maiwurm. All of them did, of course, the work. And I have the pleasure just to present it now within this little presentation. So, mixing of viscoelastic fluids, strange topic, and science and beauty maybe even sounds more strange, but I hope that I will be able to convince you that there is also beauty in between. So I'd like to start with the flow structures, and what I'm going to present first is just a very simple video. So you see here the sketch, what we're doing. We come back to the Russian turbine. We have a tracer, we have black light. And what we're observing for a stirrer speed of 10 RPM is shown here. And we are using xanthane gum, a typical viscoelastic fluid. And you will see a very strange behavior here of our liquid. So the liquid turns upwards, recycles back, radial into the stirrer again, and you see there is something like a compartment that's building up. And if we go further, if we increase the velocity, this effect is changed. So what we see still, there is a flow structure occurring, and these wonderful eddies do exist. And we see that this is typically for a viscoelastic fluid, because otherwise we have a radial Russian turbine and not an actual one, which tends to induce a flow upwards along the axis of our stirrer. So when we look more to details, we will have a look, and here you see the structures just in terms of images, and you see that the flow patterns do change from the originally elastically driven vortices, we go back or go further to some intermediate stage, then later on to something where we find that inertial forces are more dominant than the viscoelastic forces. So we see this typical structure in viscoelastic fluids, but when you look to the literature, you will find that this is already known. So you see here some sketches indicating the same strange circulation, the building up of various compartments, or in this case, even caverns, because they use liquid with yield stress. And maybe this is the opportunity for me to give a small remark to all younger colleagues in mixing. Wherever you go, you will probably find out Alvin has been there. So you see here in the list, Alvin has been among us, and 40 years ago. Nevertheless, the liquid has been a little bit different. Anyway, the mixing efficiency is, of course, highly influenced by the elastic flow compartments or by the flow pattern in total. So we did some investigations, and I'd like to show here just the specific rheological data that we found. We used basically xanthan gum solutions and CMC solutions. And what you find here is the classical dynamic viscosity over shear rate, where you see here the description. We have a shear thinning liquid. When it comes now to the viscoelastic properties, we find here the storage module and the loss module over the angular frequency, so clearly indicating that we have a viscoelastic fluid. And last but not least, we find here the first normal stress difference as indicating here. So it's the difference between the stress tau XX minus tau YY. And these liquids do behave here in such a shape. And this is just to give you an overview. And now we in chemical engineering would like to have dimensionless numbers, and these dimensionless numbers, first fluid dynamic means always Reynolds number. Reynolds number, of course, is a little bit difficult here. We have to take the shear rate into account, but that's possible. We also have the Weissenberg number, where now the first nominal stress difference is related to the shear forces. So it's more elastic forces over viscous forces. And we also find an elasticity number, where we have once again the first nominal stress difference over the inertial forces. We will find that number later on in further descriptions. Now, first experimental results, we will have a look at the size of the compartments, and this is done in the following way. We see here the size of the compartment divided by the stirrer diameter, and we've done several investigations where with a more or less Russian turbine over the stirrer speed, we see there is, well, no clear conclusion. Stirrer speed obviously does not bundle all the data. Of course, we have to consider that at a certain speed, the diameter of our compartment equals the diameter of the tank. So that's the limit. If we are using instead the elasticity number as defined before and use the same description, we find that all these data collapse fairly well on a straight line, and that gives us an idea that obviously elasticity number is a reasonable number, at least for describing the size of those compartments. Now let's go more to detail, because that was more qualitatively. Let's have a look at the velocity fields that do occur. We did some investigations here by using a laser light sheet and adding either various additives, various tracers, just to do LIF or PIF measurements. Here, this video just shows you the development that does occur if we are introducing here tracers, and you see the clear development of this kind of compartment. But we see on the other hand that there is a flow downwards, which is also a bit confusing, because flow downwards from a Russian turbine, that is something we normally do not know. It normally goes upwards, not downwards. Once again, a typical effect of our viscoelasticity. So there is a bunch of measurements we did, and what you see in all these cases, that there is here the vertical position over the radius of our stirrer. Here we find the radius, and we have made various images prepared by PIV measurements. And so I just want to pick only a few. So these are various liquids, CMC going to xanthan with various concentration. And let's start with that particular picture where we have a very low speed and a relatively high viscous medium. And we see here that if we have a look at this kind of vortex, we see that there is a flow upwards and that there is a flow downwards. So we see a typical elasticity-driven vortex. Of course, this changes. The higher the stirrer speed, we see some additional vortices caused by inertial forces, and the higher the stirrer speed, the larger are those. But nevertheless, there are still some regions where we find this typical behavior of our elasticity vortices. Let's go further here downwards. So we have here a low viscous medium, still viscoelastic. So we see once again the typical elasticity-driven vortex, but we see that with increasing stirrer speed, we see a behavior which reminds us much more to the flow field that we know from our Russian turbine. So let's have a closer look. So this is once again, these are streamlines at a certain stirrer speed. And when we go to the details, we now see here the averaged flow field, and you now can see the various vortices that do occur. So we have here our elasticity-driven vortex, and we have here the relative velocity, which is here marked by this kind of legend. But if we have a closer look, meaning let's have the vicinity of the stirrer and do an analysis which is angular resolved, we see something completely different. What does it mean different? So the average gives us an average, but reality, if it goes to details, does look differently. So what we find out here, these are Russian turbines. So we are analyzing degrees between 0 and 60 degrees because we have 6 blades. And what we find out is that the flow here close to the blades does change significantly from time to time. We have here an inward flow, but of course we also have an outward flow. So these images really show how complicated it could be to describe these effects of viscoelastic fluids. So let's go more to the engineering data. And engineering data is, for instance, a flow number. And the flow number can be here, in this case, determined for either the range where we have basically inertial-driven circulation and where we have the elasticity-driven circulation. So if we do so, we end up with a diagram here. This is the flow number over elasticity number. And what we find is for all these various results, we see that we are able to distinguish various areas. So for high elasticity numbers, so where elasticity is dominant, we end up with a more or less constant value, which is much smaller than is the case for the range where we have basically inertial forces being dominant. So we are able at least to distinguish 3 different areas or regimes. And once again, I would like to come back to my previous comment. This line is a flow number that is known from Newtonian liquid. And if you look very closely to this very small written name, once again, Alvin was there. So we not only had a look at the Russian turbines, we also had a look at other types of stirrers. And here I would just show you the flow fields by lift measurements, where we introduced traces here in this vortex, and we also had a look at the vortex below this pitch blade turbine. And what we see is that these vortices are very clearly could be seen. They are limited, but not closely limited. This is not a closed system as in thermodynamics, but there is an open flow going downwards, once again driven by elasticity. And if we do the same analysis as before, having the elasticity number over and the flow number, sorry, over the elasticity number, we also see for other types of stirrers the same behavior: high elasticity number, a very low flow number, and a very low elasticity number, meaning inertial forces are dominant. We have a higher number. So you may have asked the question, why in hell do they operate these small stirrers, viscoelastic fluids? We will use other stirrers. And therefore, this is an analysis. We are using here the Ikato Vario blade, which is dedicated to fire viscous media. And once again, we're introducing here a tracer making lift measurements. And you will find out that, of course, we are establishing here a circulating flow. I think it's always really impressive how regular these shapes are. And nevertheless, here as a result, we have a circulation of this type. And of course, this means mixing is poor. The situation changes if we are using another liquid which is less elastic and less viscous. So we see here for the xanthan solution that the mixing is much faster. But when you look to the details, you will still find from time to time this kind of vortices that also do exist in these relatively low viscoelastic fluids. Next point, this is a very simple type of stirrer, the crossbar stirrer here, 3 inclined blades. We did some measurements on that. And if we look now to the results of these measurements, we find a circulation loop of this kind, but here close to the blades, nearly nothing, or probably nearly nothing really happens. We have here the color bar to indicate the relative velocity, which is the velocity over tip speed. Once again, having a look at angle resolved measurements, the image, the picture changes a lot. So once again, we see that the flow field, of course, changes, and we see a lot of fluctuations. And especially when we talk about CFD, which we did in the presentation of Francesco, we have to have this kind of results for validation. And we did that not only for this type of cross section, but we also have the circular cross section of the tank as well, just to have enough data, because we also want to do CFD simulation, and we did. In that case, viscoelastic properties are a wide range, really wide range. And so we tried to use 2 models, Giesecke, Fantin, Tanner, and we had some measurements and we had to determine some parameters, which we did. And then we set up a viscoelastic CFD using an in-house solver based on open foam, a viscoelastic flow solver, and a sliding mesh. And what came out are images this like. Once again, a lot of images. I just wanted to highlight that we are able to determine here, what you see are various stirrer speeds increasing from top to down. And we see here the measured data, our elastic vortices, which are represented fairly well by both of the models. In the case here, where we have here an first inertial driven vortex, you see that one model, the Giesecke model, is not that appropriate here. PTT is better, but when it comes to higher velocities, both models do lead to reasonable results. And I just want to highlight that with a bunch of other data, but not to go much to details. Here we have the radial velocities, once again for various stirrer speeds, and with certain distances here from the stirrer. And this is only to demonstrate that we are able, using this kind of simulation, to end up with reasonable data for this radial velocity. Last point on my presentation is something which might be a little bit weird: side entry impellers. Why side entry impellers? We did some investigation on biogas plants and the mixing efficiency. And when we did that, we found this typical arrangement of propellers immersed into the liquid, which reminds us to side entry impellers. And then we had a closer look at the rheological behavior of our substrates in the biogas reactors, and we found out that they are not only shear thinning, that is something we know very well, but they are also viscoelastic. And analyzing that, we have here the various modules, the storage and the loss module, and therefore we thought it's necessary to have an investigation, and we built up a setup, a basin 1 meter length and here 25 centimeters high, so that we are able to determine the flow that is introduced by such a propeller. Just to give you an idea, once again, a live image. So starting at a very low velocity, very low stirrer speed. So you see there is an actual flow, which seems to be very well. And then we increase the velocity, and now things are turning. So the flow field shows a redirection of the flow. And we see here that our flow outwards is now more radial or semi-radial. If we increase it even further, we have more or less something like turbulence. And here, this is the outcome. We have images, the flow fields, we have various stirrer speeds, we have the same medium. So at the beginning, low stirrer speed, we have axial flow, then we have radial flow with an axial flow going to the stirrer. And then if we increase the velocity even further, we once again have axial flow. Okay, so we are also able to use the elasticity number to describe what we have seen. So this is the jet angle here, and we have the elasticity number here, and we see that the jet angle opens only in a very limited area of elasticity numbers, and we could describe that fairly well. We could also describe, once again, the flow number fairly well. We used various stirrers just to be sure that these results are really reasonable. We also did some CFD simulations, and here we find the outcome of the CFD simulations. Here, these are PIF measurements, and this is once again an example looking at colorful pictures. Well, it's nice, it seems reasonable, but the question is, does it really fit together in terms of numbers? So quantitatively. And this is the quantitative analysis. So we are in the range where we have a semi-radial flow. And what we have here are the flow fields, the radial, the flow field with increasing distance here from the stirrer. You see it here, or it's very difficult to see. Anyway, we have here the measured data, and not going to the details. We tried Newtonian shear thinning liquids, and when we use our viscoelastic model, at least we could describe data more or less accurately. It's not perfect, but we could describe it. The other rheological descriptions do not fit, and they do not give a reasonable answer. So, and that is shown here. We are able to once again have the flow number over elasticity number. This is something we have shown, and also our simulations do fit fairly well. And this is even more visible here, where we have the flow, the flow rates that are caused by the stirrer, the simulation over the experiments, and you find here on the straight line that they really fit very well together. And just for indication, thinning, a description, or even Newtonian do not lead to a result which is comparable at all. So then, some curiosity, we did measurements and found out that we could measure these velocity fields. That's not surprising, you have already seen that. But these measurements were done for the same liquid, with the same properties, for the same stirrer, and, which is more impressive, for the same stirrer speed. And that confused us a lot, because we thought, how could this be? And looking at that more detailed, we found out that's a question whether we increase the stirrer speed, then we ended up with semi-radial, or decrease the stirrer speed, then we ended up with an actual profile. And that is shown here in this diagram. We have here the jet angle over the stirrer speed. And when we start with a low velocity, increase the velocity, we first have this semi-radial pattern, which is still existing. The higher the stirrer speed, we will end up somewhere where we only have this actual flow. But the interesting point comes now. If we go backwards, we stay with this actual flow and only go back here at this point. So there is a clear hysteresis to be seen, and the hysteresis is also related to elasticity number. Once again, this plays a role and shows us that this obviously is an interesting parameter. I would not like to say this is the only parameter, because viscoelastic properties are so broad, but it's a reasonable one. That is what I would like to say. So looking at the other cross section here, perpendicular to the jet, we see the two conditions. That is the actual flow, and that is the semi-radial flow. And when you look to the details, hopefully to be seen, we see that there is still a very high rotational speed to be seen here, which leads, of course, to normal stresses, whereas here there are only radial flows that can be seen. So obviously there is a distinct change in the flow pattern, which of course could be used. And the last experimental results are here. We had a project where we thought of a biogas plant and whether we can use the measurement of the thrust that's acting on our propeller to have an idea of the intensity of mixing. And therefore, we did some experiments measuring this in a relatively large size tank that we built. And then we found out that having here the flow rate of the impeller and using this force that was measured and dividing it by the terms, as you could see here, gives us a collapse of all data, at least if we're in the inertially driven range. Here, this is the range, the transition where this is hardly possible. And what is now the link to mixing? Well, we did some mixing experiments, a decolorization experiment, as it's probably well known to all of you. We did an image analysis to find out, or just to have accurate measurement of the mixing time. And then when we looked to the mixing time, here we have the mixing time for 2 mixing degrees, and either 75, even 72, and, oh, well, it's a little bit distant for me, 2 different mixing degrees. And if we now are using here the reactor volume and divided by this term, which represents the flow rate inside the tank, then we have here something like, oh, what is that? So I will try again. Where is my image? I'm afraid I have to go back. I will try it differently. So I have my image back, and I will now share my screen again. Sorry for the interruption. So are you able to see my screen again? No, okay. So next try. Does it work now? Okay, good. So I just have to go where I was. So here, this is the analysis. And here we find the mixing times, and the mixing times do really well relate to this kind of circulation time. And of course, depending on the degree of mixing that was said, we find the lower times for the lower mixing degree and the higher times for the higher mixing degree. So that is something which really made us happy, because this is an opportunity to help operators of biogas plants to operate their plants systematically. By this, I would like just to resume. I hope I could show you that there are various regimes that we can find here, and the flow patterns differ in their mixing behavior and, of course, in their mixing efficiency. We have the elasticity number as a dimensionless number, helping us to describe fluid dynamic phenomena. We have side entry impellers with a hysteresis, which could be used for practical aspects as well. And we are able to even simulate the viscoelastic flow inside these tanks based on CFD. So by this, I would like to thank you. But first of all, I would like to give my congratulations to my friend Alberto. And as you see, we've been already together in Toulouse and not preparing for this award today. But anyway, this is a very nice picture and wonderful possibility to remember those days in Toulouse 3 years ago. Maybe the elder people do know that in the past we met each other in presence. And by this, I would like to thank all of you very much for your kind attention. Thank you so much.
Thank you very much, Matthias, for the very interesting, fascinating work that you presented us today. I'm sure there are questions from colleagues, and I already see a question in the chat. So I would like to read the question of Santosh Gupta to you for starting, and then I will have my own question as well. Thank you, says Santosh. According to your study, which location is ideal for side entry impellers to provide uniform mixing in least time?
Well, you know, biogas plants coming from mixing industry, we normally invest something like 500 watts per cubic meter just for mixing. In biogas plants, this is roughly the output that we can get from those. So the challenge is to mix a tank of 5,000 cubic meters or what with only a very, 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 very small amount of energy. That's really the challenge. And we have two problems. We have the substrate that must be mixed in. We have some sedimentation, and sometimes we even have something like a dense layer on top of the liquid, and both have to be mixed. And that is the challenge. And by these submerged impellers, which can be shifted in their height and maybe in the orientation of the jet, people hope to be able to reach a mixing that is sufficient with a very, very small amount of energy. And that is the challenge, and the thing that we are investigating in an ongoing project is whether we could have an idea of the situation inside the tank by simply measuring the thrust of which is acting on the impeller.
Thank you, Matthias. It's a very challenging problem. I don't see any other question in the chat. Therefore, I would like to ask you an additional question concerning biogas, since we are talking about these digesters. You presented us very interesting results using optical techniques. I was wondering if you can suggest us an upper limit for the adoption of these techniques, since probably in the biogas reactors we have also to consider that there is an evolving rheological behavior, and maybe there is an upper limit with these model fluids that we have to consider, and then switch to other techniques that are necessary for opaque systems. Is it an issue or not?
Yeah, of course, this is a big issue. Rheological behavior of substrate in a biogas plant do differ a lot, depending on whatever you're filling in, on whatever type of the year, whatever substrate, and the substrates are. So this is a huge field. So what we tried were to find some model liquids, which of course offer us the opportunity to have optical access to what's happening in the system. And of course, the accuracy that can be reached with model substances is not over the total range. We're just getting some ideas what's really happening. But I do know that for the biogas plants, where basically the only impression of speed that you can get is looking from top through a glass and just see whether there is any movement on the upper liquid level, which is very difficult to see sometimes. So there is nothing, but there are more flow followers are used at the moment just to get a better idea of the behavior of the liquid. And this may maybe help us to find out whether the model liquids that we are using are really representative well, what's happening inside these biogas plants. So that is our approach, just to get at least an idea of what's happening in these very complicated liquids.
Thank you. That's already very complicated like that. And I was wondering if you have any suggestions about CFD as soon as we add a Reynolds number that approaches transient or turbulent. Is there any additional issue with respect to poor laminar flow? Because I've seen very nice agreement between experiments and simulation, and I didn't catch the flow regime is always laminar, or did you consider the range of laminar, transitional, and turbulence? And do you have any suggestion about these tackling these different conditions?
Well, in a small tank size, it's always easier to be laminar. Yeah. And basically, I think what we see are laminar flows because they are so very regular. Even if we have this outward flow, it really is quite boring because it's all the time the same. When it comes now to the larger tank sizes, there we really have to ask ourselves the questions. I do agree that at least in the vicinity of the stirrer, or whether it's a propeller or whatever it is, we will probably find turbulent conditions. And that is something we haven't had a look at up to now. This is still something which must be done. And this may lead us to a two-zone model, which is quite often used when we have the vicinity of the stirrer and where we have other conditions than in the remaining part of the reactor where nearly nothing's really happening. Yeah? So this could be an approach, but we haven't had the time to test this.
Okay, thank you very much, Matthias. We have now a question from Adam Kowalski in the chat. Do you think that elastic effects are much more common than we realize? Is it the norm as we look at more complex products and processes?
Well, when we first spoke about viscoelastic fluids, we thought of food industry and not of biogas. I heard the first results of my co-workers and they said, well, we observed something which is strange. Biogas could be viscoelastic. And I said, well, with your setup, it's not really reasonable to measure that. We will buy a new setup and we could really find out that there is a viscoelastic behavior. But of course, once again, this will strongly depend on the substrate that you're using. Yeah, this has to be very, very clearly said. And I'm not going to say all of the media in biogas reactors do behave viscoelastic. They will probably all behave shear thinning, but not viscoelastic. That really depends on the substrate that you're filling in.
May I make a comment? Because I think, first of all, I'd like to say what a fantastic visual display you produce, Matthias, which you always seem to do with your students. But
Lena does as well.
You've also hit the nail, I think, very firmly on the head. You showed a slide from work we did many years ago, and that was all meant to tell us about what happened in big viscous bioreactors making xanthan gum. But by the time you get to the large scale, it's all turbulent. And I'm not sure how much what we can learn at small scale really tells us. It's, I mean, I hardly ever find that work now useful because it's, they're all, you know, you talk to people like Stuart Stocks and when he was at Novozymes, and the Reynolds numbers are pretty turbulent. Very interesting, quite a challenge. Anyway, lovely talk, thank you.
Yeah, thanks for the comment.
We have questions from Alberto and Claudio now.
Yes, well, mine, well, but Claudio raised his hand before mine, so please, Claudio, go on.
Oh, no, you can go first, it's fine.
Pardon?
You can go first, it's fine.
Okay, thank you. So mine, it's not a question really, it's just, first, I wish to thank Matthias for the very nice picture he presented, which is still on show. I had forgotten that picture, Matthias, which demonstrates that although we are of more or less the same age, my brain is definitely older than yours. And the other thing that I wanted to say, well, and I wish I add that I'm really glad to share today this prize with you. And the other thing I wanted to point out is that what amazes me about your work, and this is something I already said when I attended Lena PhD dissertation, is the bravery, the courage you have in choosing to tackle these extremely complex phenomena. You need a courage which is not commonly found. So I wanted to point out the courage with, apart from the technical and scientific excellence, there is courage behind your activities. Okay, that's it. This was my comment.
Just a short comment to that. Only one keyword: curiosity.
Yes.
Very good.
I will get to it.
Yeah.
Matthias, fascinating work, and congratulations on your award. I'm just wondering if viscoelasticity in stirred vessels is always seen as a challenge, or if it is any route to use elastic turbulence or elastic instabilities as a mechanism to enhance mixing in stirred equipment.
Well, in one of my lectures, I'm showing what does it mean to have laminar mixing. It means it takes a long time. So you have these lamina and they just pass by, and there is no vertical flow in between, no real convection. And therefore, I think we have to deal with that. I do not have an idea whether we could use it in a positive way. I would more say we have to be aware what's really going on, and we have to decide which type of stirrer has to be selected pretty well to solve this problem. So that is something which comes to my mind first when I hear this question.
Thank you.
Well, Matthias, one additional question. I was very astonished to understand that fluids do have a behavior. So the hysteresis you showed, I was thinking if that might be an effect of mass inertia, or what would you understand? What would be the explanation for that kind of hysteresis in that fluid?
Yeah, quite difficult question. Therefore, maybe I do not have a clear clue. Therefore, I showed the situation of the cross-section of the jet, where we saw on the one hand side, there was a very, very strong tangential flow. And whenever we have this tangential flow, we have normal stresses. That is typical for the viscoelastic fluids. And maybe this stabilizes the actual flow much more, so that we can even go down with the velocity and we still have stable conditions. So that would be my first guess how to explain this kind of effect. But of course, we are still working on that, trying to find out whether there is any further time dependence. We just think of the pool, which seems to be large in comparison to the stirrer, but that is still some research that is going on.
Okay, thank you.
Thank you, Matthias. Thanks for all the interesting answers to our questions and for the presentation. Congratulations again. It's time now to listen to Alberto's presentation. So, Alberto.
Thank you, Josie. I'm trying to share my screen now.
Yeah, we see it.
Okay. And no, this is what I wanted to show first. So, and let me start the presentation. And let me just briefly introduce it. So let me first of all thank the award committee of the working party, our members, and the member that advanced my nomination. So and let me say how honored I am by this prize, and I already said that I'm also glad to share it with Matthias. And thanks to Alvin and Ellen, and I'm really glad that Ellen's name is part of the, is explicitly made, because she, no doubt, is definitely part of the mixing community. And so she deserved to be there. And so I want to thank Alvin and Ellen as well and Alvin especially for these kind words on what I have tried to do along these years in mixing. So getting to the topic, well, no, I have other thanks to do before going on. And these are to all the colleagues that variously contributed to this, to the things we did. They are listed here. I won't read all of them. And the last one, you know, she's with us, and she certainly made an important contribution to the CFD side of our work. So, going to the topic of my lecture, let me say that, well, I wondering about what I should show today, I found that, well, I thought that there was nothing really entertaining among the last things we did, nothing comparable to the beautiful videos and images that Matthias just shown us. And so I decided to rather go for quite old things. The first things we did in the mixing research, hoping that for the young people that is following this conversation will be new, and that for the elder people that might have been in touch with this stuff, so many years elapsed that they may see them as new as well. So that is my hope, at least. And so we'll talk about mainly early work on mixing we did. And but before going to this, let me spend a few words about curiosity itself. You can see this image. This is an image of a book I came across recently. And curiosity is certainly a powerful driver for us. That Matthias just reminded us this, and powerful driver for academics. So I was intrigued by this book, and I can recommend it. It's a book entirely dedicated to curiosity. And it's by, actually, Mario Livio is an astrophysics professor. And I must add, I may add, he's not Italian, despite its name. He was actually born in Romania from Jewish parents. And then he moved in Israel, where we had his education and started his academic life. to move then to the States at Johns Hopkins University. So it has been a very, very important professor in astrophysics. And at a certain point of his career, he became interested in other things with respect to astrophysics. And one of the things he got interested in is curiosity. So his words are, he became curious about curiosity. And in the book, there are several questions addressed. Is curiosity a human feature? Do we share it with animals? Tells about the two most curious men in human history, according to him at least, that were Leonardo da Vinci and Richard Feynman. And the various types of curiosity, the one that interests us most is epistemic curiosity. The curiosity that is driven by the need to know more about nature, about the world. And it's what, and this is the curiosity that affects us as academics most. And from that book, I only took this graph, this inverted U graph, where you see there are, well, this is obviously a very qualitative graph that depicts how curiosity varies and how does it depend on knowledge of a certain topic. When you know nothing about a topic, your curiosity is very low because you don't know that you don't know a lot of things. You may not know about the topic itself or the existence of the topic itself. So there is very low curiosity or zero curiosity when you know nothing or little about a subject. But when you start knowing something, questions arise and you discover there are many unknowns. And the more you know, the more unknowns pops up. And this drives the curve up in the curiosity versus knowledge graph. On the right side of the graph, you know a lot about the topic. There is little room for unknowns, then curiosity decreases because there are not many unknowns to address, and declines. And this gives rise to this U-shaped curve that I found that describes very well the way in which my curiosity for unbaffled vessels went on along the years. And so I like to show this graph to you. Well, I must say that this is the original picture in the book. I'm not sure it goes down like this. It may go down like in this exponential way, but nevertheless, this is a qualitative graph, and I liked it a lot. So going back to many years ago, I was already working on mixing issues because Italcali, a company operating a salt mine in Sicily where they produced a fertilizer, potassium sulfate as a fertilizer. Well, in their process, there was one of the steps of the process was dissolving a double salt named, well, I don't know the English name exactly. I think it's something like skienite. I guess that the German name is Schönheit or Schönite. The Italian name is Schönite anyway, but in English, I don't know how to pronounce it. Let's pronounce it skienite, as the word ref suggested me. And when you dissolve it into water, what happens is that while the solution continues and the concentration of skienite into water, well, skienite ions into water increase, at some point, the solution gets saturated, but not towards skienite, but rather gets first saturated with respect to K2SO4. So crystals of K2SO4, the potassium sulfate, start being produced while skienite is dissolving. they call this step a conversion of kyanite into potassium sulfate. It's clearly a fairly complex process if you want to model it, because you have the dissolution and the crystallization coupled. So they asked us to try to do something for modeling this process. And we started doing it by looking at dissolution first. And we immediately had to face the circumstance that the datum on kyanite solubility was not available in the scientific literature. And it was so just because you can't measure it, just because you can't get a saturated solution with kyanite into water. So, and these are very concentrated solutions, so they are highly non-ideal. So in any case, the datum was not available at all. Then we knew that we needed a way to measure interfacial concentration of kyanite during its dissolution. Actually, this was the quantity we really needed, not its saturation concentration. But as you know, it is usually assumed in mass transfer processes that at the interface you have equilibrium. Then the interfacial concentration should coincide with the saturation concentration. But what we really needed for modeling purposes was the superficial, well, the interfacial concentration. So what we did is that we devised a simple model. The model assumptions are very reasonable. Probably the most difficult to accept is that Kc, the mass transfer coefficient, is independent of particle size during the dissolution. But it turned out to be a very good representation of the reality. And we were even able to get an integral analytic solution for the concentration dynamics in the system. In these formulas, Xi is dimensionless concentration of the solute system. A is a parameter that involves several constants and the mass transfer coefficient, which was part of the problem. Y is another concentration which is related to X, and it can be shown to coincide with the ratio between the instantaneous value of the particle diameter and the initial value of the particle diameter in the system. And I must say that the model worked extremely well. It was able to represent the concentration dynamics dissolution very well. Clearly, we kept far away from the saturation in this data, but we were able to actually measure the interfacial concentration, which is embedded into this parameter Xi, and that luckily turned out to be the same in all our experiments, independently of initial particle size and independently of agitation speed. So we were confident that was the actual interfacial concentration. Well, obviously the best fit curve is the black one. The other two curves were meant only to look at sensitivity. How would have the curve change for a 20% change in the value of mass transfer parameter? You do get the red curve, or by changing into opposite way the two parameters, you get the blue curve. As you can see, the model and the physics of the system is quite able to resolve the things with and get the values of the mass transfer coefficient and that of the interfacial concentration within a very few percent precision. Notably, we used it also to look at the dissolution of sodium chloride particles, for which the datum on the interfacial, on the saturation concentration was available. And the measured interfacial conservation did actually coincide with saturation concentration. And by the way, this is one of the very few experiments, or very few proofs that our common assumption of no resistance at the interface and of equilibrium at interfaces has been obtained. So we were working in this field, and for this reason, I may say that our interest started, well, the interest towards mixing issues and to solid suspension had just already started. And in this realm, we came across to this paper by Hohl et al., where authors claimed that higher solid liquid mass transfer coefficients could be obtained for the same energy input and stir vessel in unbaffled vessels with respect to baffled vessels. This intrigued us. This raised our curiosity, as I said, and the explanation offered by the authors was that this was probably due to a matching between the energy dissipation map that, according to them, they expected to be stronger near vessel walls, and the particle concentration map. So the idea was, if particles do stay in regions of the vessel where the average dissipation is higher, and therefore the average mass transfer coefficient is higher, then you will get a higher average mass transfer coefficient in the system. And also this explanation intrigued us. Was it true? The subsequent question was, can we exploit it in order to further stress this phenomenon and get even more efficient systems? As well, our curiosity was, at least at this stage, at this point, maybe higher than this, along the curiosity knowledge curve. And first of all, we tried to see whether actually mass transfer coefficient did increase for the same energy dissipation rate in the tank, and we found that yes, this was the case. At least this was the case when potassium sulfate was used as a solid phase to be dissolved, while when using benzoic acid, which is almost isodense with water, then we could spot no difference between the baffled systems and the unbaffled ones. But up to now, the picture depicted by Hohl et al. Was still holding, and so we went on and we tried to exploit this by concentrating dissipation into a wider volume. So we tried with this to deploy along the smooth walls of an unbaffled vessel a net, a star-shaped net, or simply deploy a net along the wall in order to have a further increase of turbulence there where the particles were supposed to stay. And we also used several stirrers, apart from Rushton turbine and PBT, a quite tall stirrer which occupied most of the vessel height, and another stirrer which was tall, not as tall as the former one, but definitely much wider, in order to see whether this had an effect. And these are the results we got. Here, let's first look at the results obtained in the simple unbaffled vessel with smooth walls. As you can see, no matter which stirrer we used, of the four I mentioned, you got more or less the same data, the same results in terms of mass transfer promotion. So we took as representative the one obtained with the Rushton turbine, and the same data are reproduced in all other figures for comparison purposes with the results obtained with other systems. This is the comparison with standard baffled tank, and as you can see, once again, the difference is important. There is the expected difference. The StarNet lined tank, well, was rather disappointing, I must say. It was even less efficient than baffled tanks in promoting mass transfer. And more or less the same was true for the just with deploying the net along vessel walls. Once again, efficiency typically decreased, apart from the case of using that very strange, quite tall and very wide stirrer, but there was no point because at most it's as effective as a simple Rushton turbine in an unbaffled vessel. So there was no advantage at all, and we had to live with it. So at this point, we had come across a number of issues that concerned unbaffled tanks and discovered that they were substantially unknown. Not even power demand was decently, could be decently estimated. There were few data, but not many. Particle suspension, 0 info at the time. Mixing rates, nothing. Gas liquid performance, etc. So there was a huge lots of unknown features of the unbaffled vessels. And therefore, our curiosity at this point was definitely at maximum. We knew that there was lots of unknowns. And in the last minutes of my presentation, we'll try to address some of the things we did over the years. Let me just stress that it's not easy to get this fundamental research funded. It's very difficult to get funds for it. So this research went on from time to time typically by stealing money from other research lines, other research projects. And whenever a student popped up that would volunteer to carry out some research in this field. So it took decades really, just because we couldn't concentrate on it completely. So, but over the years, we got a number of results. And well, let's start with power demand. There was some information, we hadn't got time, but I'm sure you all remember this curve in this graph, which was derived from original Rushton's data for the unbaffled vessel, and in which the correlation implied using a correction factor that involved the Fruit number in its evaluation, which made sense actually. What we did in this field was that first we identified and distinguished between each other the two main regimes that we choose to call subcritical and supercritical regime. Supercritical regime is when the deformation of the free surface reached the impeller and air bubbles are steadily injected into the system. So it's a two-phase system really. While the subcritical regime is what occurs when the deformation has not reached the impeller yet. And of course, you have a critical regime in between the two, which marks the transition between the two. And this is important for power demand, because if you look at these power number curves obtained with two different viscosity with liquids, you see that there are neatly two different behaviors, two different dependencies of power number on Reynolds number. And the knee in between the two is exactly where air starts getting injected into the system. So it's the transition between subcritical and supercritical conditions. And so the two had to be separately correlated. And if you look only at the data obtained in subcritical conditions, they line up remarkably well around a single line as a function of Reynolds only. This quite surprised us. We actually expected that Froude number would get involved, but there was no need, neither a way to improve these results by letting Froude number have a role there. So a very simple correlation, which turned out to be robust in scale up. The red data have been were taken on a larger vessel than the black data, then they line up remarkably well. As regards the supercritical conditions, luckily enough, they also lined up very well and robustly well on scale up with this simple correlation that involves this time not Reynolds, but the product Reynolds time Froude number. This is the result. These were the results. So they interpreted very well all of our figures. And we then proposed as a complete correlation, a correlation that says, look, at any Reynolds number, due to the behavior of the curves, you can compute the power number either by the subcritical correlation or by the supercritical correlation. And all you have to do is to get the smallest of the two figures. Also, the correlation you select in this way tells you which is the regime you have to expect to be at that Reynolds number. So this marks also lets you know whether you are in a subcritical regime or a supercritical regime, and it works very well. So let's skip it. I won't say much about particle suspension. You all know, probably these are better known info we produced. Unbaffled tanks, in short, turned out to be much more efficient than baffled vessels with specific power demand to reach the just suspended condition that were 5 times smaller than those required by the most efficient stirrers in baffled vessels, even when in the unbaffled vessel a simple Rushton turbine was used, which, by the way, turned out to be a very efficient impeller for solid suspension in unbaffled vessels, probably the most efficient way. But I don't know whether you saw this graph. We found that this is true. Unbaffled vessels are more efficient than baffled vessels. And the Rushton turbine is more efficient than other stirrers, even for very high concentration solids, for which you can introduce a concept like the power required to suspend a kilogram of solids. This is a very important question when you have to deal with, let's say, bioslurry reactors for soil remediation, or mine processing. Suspending the particle, getting them involved into mass transfer with the minimum possible energy is a very important issue there. And as you can see, the amount of energy needed to suspend a kilogram of particle at first decreases and then increases, giving rise to a minimum, a relative minimum, in which you have a minimum energy input to suspend, a minimum on this concentration, solid concentration axis, a minimum energy demand to suspend the solids. And this turns out to be around 20% for medium-sized particles and about 30% for the larger size particles we used. But in any case, you can see that the blue curve that represents the results obtained with Rushton turbine is below the others. Rushton turbine is very effective at solid suspension, also in unbaffled vessels, also for very highly concentrated systems, high concentration of solids. And I think I ran out, almost ran out of time. So I will just give you some information about mixing times, which are the thing that worries most people when you say, why don't you use an unbaffled vessel? Then the first answer you get, mixing times, well, you expect unbaffled vessel be poorer mixers than baffled vessels, and they actually are. If you look at them in terms of power efficiency to mix, to get a certain mixing time, these are the thick black line represents one of Alvin's correlations for baffled vessels. So it's representative of baffled vessel results. And as you can see, depending on the type of impeller, you have performances which are, mixing times which are from 3 times to 5 times larger than in baffled tanks. I'm not sure this is an issue for many processes. We have been talking yesterday about biological processes that usually have time constants which are in the days range rather than in the minutes or hours range, days range. So the fact that the mixing time may be, well, several tenths of seconds rather than a few seconds shouldn't be a problem there. But the thing that most surprised us here is that if you go to fairly high power dissipations in the tank, in these points, which not by chance are the last ones we examined, these are the points at which the system becomes critical. The vortex reaches the impeller. Well, because this was the last velocity at which we could use PLIF to measure, to assess the mixing time. Afterwards, bubbles got injected in the system. But in this case, quite surprisingly, unbaffled vessels became as efficient as baffled tanks. And this was quite surprising to us, and I hope surprises you too. And if I have a couple of minutes more, mass transfer, gas liquid mass transfer was not an issue at the beginning, but then we consider that the large deformed surface typical of unbaffled vessels may well help oxygen to get in. And for weak cells, for shear sensitive cultures, for which, as you know, bubbles are a problem because when they burst, they tend to damage the cells. We wonder whether using an unbaffled vessel, exploiting well, not very large, but relatively large surface, interface surface with the gas over the liquid, you could get enough oxygen to sustain, for instance, mammal cells. And to our surprise, yes, the answer is yes, there is a quite wide range. Well, on each of these curves, the solid points, the solid datum marks the transition from under critical, so subcritical to supercritical conditions. So all these points were obtained in subcritical conditions with no bubbles injected into the culture broth. And the red line indicates the minimum KLa required to sustain molecular, small mammalian cells, for instance, at the usual culture density, culture concentrations. And as you can see, there is a quite wide range of conditions in which you get enough oxygen to sustain these cultures, but avoid bubbles that may damage them. Also, the shear rates here are very low. You can see that we are talking about 100 watts per cubic meter. So you don't need to go over, and shear rate all over the tank is very low, but this may not be of concern. Bubbles are usually a concern in these cases. So I think I went over, so I don't steal your attention anymore. Let me just say that after having answered at least a significant part of the questions we had come across, we are now in this position on the curiosity versus knowledge curve for unbaffled vessels. So I hope that at least my collaborators will still follow this path. In my case, I'm afraid I'm just going just there. I'm too old to be really still very curious about this. I must do like Mario Livio did, start getting curious about possibly very different things I had not thought about earlier. Okay, then I thank you for your kind attention and thank the organizer for everything.
Thank you, Alberto. I'd just like to congratulate you, like I'd like to congratulate Matthias and Lena and Francesco. Lovely presentation, and I love the start of it, and it's typically Alberto to start with something a bit philosophical like that. And I think that you've given me a nice idea for a book on my summer reading list. Thank you. So we have a question from Ji Wu in the question and answer tab. So he asks, so solids mass transfer rate decreases without baffles. Is this the same for power input?
Of course, when you strip out baffles, the power required to stir at the same agitation speed decreases. So can you repeat the question? I might have got wrong it.
Okay, and he says, so solids mass transfer rate decreases without baffles. Is this the same for power input?
Well, it doesn't decrease. Well, if you look at it on the basis of the same agitation speed, it may decrease. It probably decreases. But if you look at it on the basis of the same energy input, in baffled vessels, it's always lower than in unbaffled vessels, or at least the same if particles are isodense, as I told you.
Okay, thanks. Matthias, you have a question for Alberto.
Yes, Alberto, thanks for the presentation and for the courage. I will take the word you already mentioned when you spoke about my presentation, because I think you're one of the very, very lonesome supporters of unbaffled tanks for turbulent systems. My question is the following. You showed that there seems to be an improvement of mass transfer for solid liquid systems, which means that there is something happening at the tank wall. And if there is, well, increased shear rate or whatever it is at the tank wall, does not that necessarily mean that for cell systems, these ranges must be very serious because they could damage the cells?
Thank you, Matthias, for the question. Well, my guess is that probably it's not true that dissipation concentrates in near vessel walls. What I think actually happens is that, and this happens only with heavy, relatively large particles, they definitely are pushed by the centrifugal field near vessel walls, and from time to time, they touch the wall. This slows them suddenly, and for a short while, they experience a high relative velocity with the liquid phase. And that, on the average, makes up for that 30% increase that we observed with large, heavy particles in the tank. And that's why putting a net on the sidewall didn't work at all.
Okay, thanks.
Okay, we have another question from the a participant. So they say, we usually see reduced power draw for just suspended in an unbaffled system compared with baffled conditions for solid suspension in low viscosity fluid. Do you see similar results?
Yes. I mentioned that. I mentioned that with it. I didn't go through it, but we have found this over and over the years.
Okay, so that was it. Another question from Ji Woo, actually.
Yeah.
May I make
Ji.
a comment?
Yes.
I think this is very, very interesting, and I've followed Alberto's work. Never been 100% convinced, but I'm getting more and more that way. And I think one of the problems that we have had with mixing is there was a lot of mythology developed by, well, perhaps it's too strong, but by Messrs. Rushton and Oldshoe. And I think in the case of Jim Oldshoe, he was more an employee of Lightning and their research director, and they wanted everyone to go to them for their work, but all the high shear, low shear concepts. And I think there's a lot in that now about unbaffled, because my early reading of the literature said unbaffled is no good. And it took a long time. As some of you may know, I did publish a paper on showing very good results with micromixing without baffles. That work was undertaken only to show how bad it was. I made Melissa Assarelli completely redo the work, rebuilt another tank, and I think Alberto, but with his persistence, has said, you know, really, you do need to look at this properly. And one of the last developments I've been involved with, pretty much at the side of it, I'm not 100% convinced, but I'm getting there, is developing a new bioreactor. Well, it's a version of what was mentioned yesterday, the Amber 250, which was developed from some work which was based out of the University College, and I was one of the people who got the work, and that working with them, and that is an unbaffled tank for stem cell culture, much like any other tank of a bioreactor, but without baffles. Other than that, it's much the same, and it gets the solids up with the lowest power. So thanks, Alberto. Great.
Right.
Thank you, Alvin, for your comments. And let me add that I was really glad to see a paper by you on this Abri something reactor unbaffled, because I thought, well, I did manage to convince Alvin in the end.
Okay, so just before we finish this this wonderful session, there's one last question from Santosh Gupta. So who asks, I can understand that when mixing time is not the controlling factor, then the unbaffled tanks do better compared with baffled tanks. But how does this apply to fluids that have complex rheological behavior?
I'll tell you, I have not been brave enough to enter into the very viscous, elastoviscous fluids. So I had not the courage that Matthias has. I never tried it. Sorry about that.
Great, thank you. Well, with that, because we are running a little bit late, but I would like to thank again and congratulate our prize winners. And I'd like to thank again all of the participants who connected from outside, and also the panelists here with us. So Gizi and Alvin and Claudio and Wolfgang, who's now left. And it was lovely to have organized these last these two sessions yesterday and this morning in one sort of a short kind of a simple replacement for not having been able to get together for the 17th mixing conference, European Mixing Conference, which was meant to be held in Porto this week. So we'll have to wait until 2023 for that now. Hopefully next year, some of us will be able to meet up at NAMF, or I think there's another ISMIP next year, perhaps. And in between time, maybe somewhere else. So thank you to everybody and congratulations.
Thank you.
Okay, thank you, Joelle.
Thank you, Joelle.
Well, thank you, everybody.